Today's session is the expert lecture on OFDM for wireless communication, and today's speaker is Sagar Somashekar, Senior Architect, Nokia Networks, Bangalore.
Yeah, very good morning to all of you, and very much thanks to all of you for joining this session. So today's topic is OFDM for wireless communications. So I request all of you to pay attention because so today you're using this technology right now in your mobile phone. So if you are able to understand the concept, then actually you will be able to appreciate this subject very well because you're already using it, right? So many of the subjects you're not using in practice, or you're not seeing the concepts in the lab, so you're not able to appreciate it. But definitely, I say that you will be able to appreciate by the end of this presentation. Okay. So I have been given module number 4, OFDM for wireless communications. So I will try to cover most of the concepts present in this module. Okay. So for that, what I will do is I will start with all the fundamentals. Okay. So whatever the fundamental concepts that are required to understand OFDM and many other wireless concepts, I will cover those things first. Then I will go to some of the OFDM basics, and then OFDM main concept with respect to single carrier versus multi-carrier, and we will also try to see the equations of OFDM and block diagram. And then finally we'll touch upon channel estimation. Okay, and I will let you know where you can find this good information at the end. Okay, actually I have not prepared any presentations as such. I usually give blackboard kind of presentation only, so I will follow the same thing here also. I hope you guys will be able to. How you guys will see? You guys can sit this side, right? Okay, all right. So what I will do is I will talk about very simple concepts, and I will try to explain the things in a simplistic way so that you guys will be able to understand it very well. So only thing is just each and every concept you just keep in attention. So first thing is we have to go back to our old days, and we need to see what was there for communicating from one distance to another distance, right? So mainly we had a telephone, and how was these phones connected? Via wire, right? So when there was a connection via wire, what will happen? The signal was embedded within that wire, and yeah, many things we didn't have many problems there compared to what we have today. So today's communication is wireless communication. So with that, what is happening? Signal is not embedded in a particular cable, right? So now signal is everywhere. So once you transmit, once the signal is transmitted out of your mobile phone, signal travels everywhere, and it will try to reach the intended receiver. So here, what do we need to understand? So if we want to draw the diagram, so what I will do. Okay, this much thickness is fine, right? So let's say I will draw the this is tower, okay, what you see outside mobile towers, and this is your mobile phone. So when you transmit the signal from the tower, then it is supposed to reach to the UV like this, but now it's not a wide connection, so it's a wireless connection, so it travels multiple paths. Okay, so let's say it goes to different path. Maybe there could be some building or some obstacles or reflector, and then it would reach the signal in a different path. Okay, so this is very simple, right, to understand and appreciate. Now here what you need to understand here is, I will not take multiple paths and I will confuse you guys. So to explain it in a simple way, I will try to take every concept with the minimal dimensions. Okay, so here what is that you need to understand? First thing is, when signal travels, because of path loss, signal gets attenuated and you will receive less power, right? This is also very basic concept. Let's say here you transmitted with P, then you will receive PR, which is less than P, because of path loss in the. So why do you get path loss? Again, it's a basic, like signal will get scattered, or when it gets reflected, some of the signal is getting absorbed, right? So one thing is power is getting reduced. So one of the factor which we need to mention is with respect to attenuation. I will say A1. So A1 is getting actually modified when it travels over the air. And what about in the other path? Other path, in fact, it has traveled a longer distance. It would have come across many buildings or many obstacles. So in the other path, let's say A2. So now, very basic, what is the relation between A1 and A2? We can write, right? So A1 and A2 are attenuation values. So since it is an attenuation, A2 is having more attenuation than A1. Okay. Now with respect to power, if I want to talk, this is P1 power, this is P2 power. So which is having more power? Direct line of sight is having more power, the P1, and P1 power is greater than P2. Okay, easy. So next, what is the next thing which we need to understand? Okay, with intuitiveness. So next one is with respect to delay, right? Time. So the one which has traveled in the line of sight path, let's say that reached in time t1. What about the other one? It took longer time, right? So let's say that is t2. So then what is the relation between t1 and t2? T2 took longer time than t1. Okay, what is the other factor which we can think of? So another one is with respect to phase. Okay, so this part will have phase phi1 and the other part will have phase phi2. Anyway, phase is 0 to 360 degree, so it keeps wrapping around, right? So we can't have the relation here. Okay, but one thing with respect to phase, so what is that we need to note? So let's say phi1. What I will write is phi1. It will reach with 0 degree phase. So there was, after traveling a certain distance, let's say there was no change in the phase. Okay. Now in the other part, let us consider phi2. That also traveled, but the distance was such a way that again phase was 0 degree. Okay. Let's say 0 degree. Now what is that we can infer? So when I say that these two signals are traveling in a different directions and it is reaching to the receiver, at the receiver, what should we do? We should actually, receiver should add them up, right? Add them up and give the signal for the further processing. But when we add, and if the signals, both the signals are in phase, they will add up constructively. Okay, this is also again very basic thing, right? If let's say the second path is having 180 degree phase shift, this is out of phase shift. And let's say if both the signal have similar amplitude, actually in practice, as you can see here, A1 and A2 are different, right? It will not be, but let's say for now, to understand, both the amplitudes are same, which means both the signals are same, but only thing is they are out of phase by 180 degree, which means that both the signal will cancel out. Then actually will not receive anything. So now you understand what is the major problem or challenge with wireless communication. Because of multipath, signals can add up or signals can get cancelled, depending upon these three factors which I have mentioned over here. But this problem was not there in the wired communication because signal travels within the cable and we didn't have any multipath there. Okay, so till this point clear, right? Simple only to understand. I did not say anything complex. Yeah, with this, what is happening? Like, so with this, there is one major phenomena in wireless communication. So that is nothing but what I will say is over a period of time t. Okay, I will plot in the y-axis SNR, signal to noise ratio, or you can just say signal power. Okay, for now, since just now we saw that the signal coming from the multiple paths can add up or can cancel out, or if they are in the intermediate phase values, they can cancel out partially or they can reduce the amplitude partially, things like that, right? So what will happen? Your signal power, when it adds up, can be high value. When it partially cancels out, it can be medium value, or it will vary actually depending upon the channel condition. It can go low or high like this. Okay, which means that your signal power is fluctuating over a period of time because your environment is changing and your multipath travel is also changing, and all of the parameters with respect to attenuation, phase and time, they are changing. That's why your signal power is also changing. So this much is clear. So this phenomena is called fading in wireless communication. All right. So having understood this, we'll move on to the further concept. So one thing which I want to mention here is, since there is a fading phenomena and it brings in a challenge on how we should add those multipath signals at the receiver. Receiver is becoming complex. Okay, in wireless communication, receiver is becoming complex because we have multipath components. We should bring in a mechanism to add them constructively or to ensure that we eliminate the phase and add them in phase. Okay. Now you might ask question that, okay, so I have considered two paths, but in reality what happens? Like, it travels everywhere, right? So you might say, why can't you consider 10 paths? So but let us say in practice what is considered. So for that only there is one more profile which is considered that is called as power delay profile, PDP. Okay, so this power delay profile versus time. Now at T0, first component. Okay, first component is considered. What is this first component mean? Okay, I will come back here. So in the channel here, amplitude, time and phase are all changing, right? So this effect we call in our academia or in our textbooks. So we simply call, okay, this particular path as H1, channel coefficient H1. Okay, but if you see what is H1, then you will get to know, okay, it is a function of all this amplitude, phase and this delay. And what about the other direction or other path? Let us say H2. Okay, so based on the equations we derived, so at T0, H1 component will have high power. This is the power, right? Power delay profile. So delay, we will see delay because every component is received with a certain delay. Okay, so first component is received with no delay and has got some power, which is a high power, we know that. And the second component, let's say received at some delay, T1, and this would have less power compared to the first one because it would have traveled a longer distance and it would have come across multiple scatterers or multiple obstacles in the path. Then third one, T2. So then it will be considered to an extent where there will be a threshold. Okay, so let's say the threshold is threshold, or so let's say receiver sensitivity would be something like, for example, 10 dB. So any let's say 10 dBm signal power we are considering. So any signal power less than 10 dBm, we will say okay, we are rejecting from the receiver. Anything above that we'll consider. So what is happening here? T2 is just touching the threshold. Let's say T3 is also received, T4, it goes on, it will be received. But the thing is that these power levels are very low, so these things are rejected, and the major multipath would be considered up to this point. Let's say, okay, this is just an example. So how many paths? We call it as channel taps. Channel taps is denoted by L. This L could be like 4 or 6. Okay, depending upon the different profiles which we consider. Right now, for the example which I have considered, there are only 3 channel taps, which means that 3 multipaths. All right. So now one important concept which we need to understand here is the last component which is received at a delay of T2, right? So what do you call from T2 minus T0? So this is the maximum delay that the particular signal has achieved, right? Which means that T2 minus T0 will become T max, and this T max is nothing but your delay spread. Okay, so it was easy to understand till this point. So actually, I'm trying to explain some of the basic concepts. All these things will help you to understand OFDM, why OFDM was required. Okay. So now I will move on to the next concept. That is, as I was telling, that when we have two paths. Let's say this is one path and this is another path, and I was telling that here the signal can go to 0 because of out of phase, right? So now if we have only one link between transmitter and receiver, what happens? So let's say I will write it something like this. So this is transmitter and this is receiver, and there is only one link, and this link because of this multipath components, this link can go to 0, right? So if it goes to 0, then you will not be able to have a reliable communication, right? But reliable communication is very much important in today's practical system, because you are the main users. Say, for example, you try to call to your friend and you see that the call did not get connect. How much frustrated you will be, right? So even a small amount of unreliability is not tolerable. So that's why the reliability should be kept at the highest rate. So now for that, what can be done? You use another link. Another link means maybe it could be another antenna. So multiple antennas. So if you use another link, then even though one link is failed, there is a chance that you can receive the signal in the other link. At least, see, in the other case, one link is gone, your chance is 0%, right? Now at least now if you have 2 links, even though one link goes, now your chance is 50%. So it increases your chance of receiving the signal if you have multiple links. So in the other link also we would be transmitting the same signal. Let's say here if I'm transmitting signal x1, the copy of the same signal is transmitted on the other link as well, so that one link goes still at the receiver, whatever is the information x1, we have received it. There is no problem. But what is the concept here which we need to learn? So this is nothing but diversity. Okay. So this is there in our next module, but since I had come to this basic concept, I thought I will touch upon the definition of diversity. So what diversity says is that, in simple words, you have a multiple copies of the same signal, okay, transmitted by some means. It could be in different antennas, or it could be across a different time. But ensure that multiple copies of the signal is received at the receiver, and the receiver is able to recover the intended signal out of that multiple copies. So out of the multiple copies, how even though one link is gone bad, the receiver should do some intelligence to get the signal from the other link. Okay. So for example, you are writing your final year project, and you have your project copy, right? So the document you will put it in the, let's say, hard copy, and you're carrying everywhere. By chance, due to fire or something, it got lost. Then how do you recover? So what do you do? So you will have another copy in the another soft copy which you would have stored in the Google Drive or something, so that you know how to recover back. So now you got it, right? You had multiple copies of the same information. One was in the hard copy, another was in the soft copy. So even one is lost, you had a chance to recover the other one. So that's how the diversity will work, and that's the definition of the diversity. Okay. Okay, moving to the next important concept based on that multipaths. So let me write the diagram. Okay. So I hope, even why I choose to be going for this blackboard is that with the diagrams, I think you guys will be able to connect very well rather than just PPT, text mode, things like that. Here I can draw very flexibly. So the thing is that, let's say signal X1 is transmitted. Okay. We had this multipath, right? So this is one path, this is another path. So in the first path, let's say at t is equal to 0, we receive the signal like this. Okay, let me not write like that. Okay, let's say 1, 0, and then okay, this is first symbol, second, third, fourth. Okay, now what is happening with the other path? Other path also I'm transmitting the same x1, right? But as I was explaining in the previous slide, there is something called delay spread, T max. So we need to consider the worst path which is coming and adding up to the existing one. So if we are going to write that signal, then how can we write? So let's say, for example, right now that T max comes over here, which is a delay spread. So then the last signal it's the same signal, right? It's the same x1 signal only. So it starts from here and it goes first symbol, second, third, fourth. 1, 2, 3, 4. Now, what is that you can observe here? This is happening at the receiver, right? Receiver, these two are received. Now the thing is that these two has to be added up in some way so that we get x1. But the moment we are going to add here, what is happening? Let's say at the second symbol, okay? At the second symbol, you're trying to recover. Let's say you're trying to recover the second symbol. When you're trying to recover the second symbol, the receiver is also seeing the signal from the first symbol, okay? So this first symbol, a portion of first symbol is actually coming at the same time of the second symbol, which means that there is an inter-symbol interference. This is clear with the diagram, right? So there is an inter-symbol interference here. With this, what is the problem? Definitely, you are not able to recover x1 in a unique way. Okay, so not to confuse here. Let's say here symbol 1 is x1, symbol 2 is x2, like that. So this is x1. Then at the receiver side, y received signal is equal to x1 plus x2. I have not written the channel. Let's say channel is h1, h2, like that. So not only x1, there is x2 as well. So there is an inter-symbol interference between these two symbols. Okay, so yeah, definitely we need to eliminate this, right? But why, first of all, this particular inter-symbol interference is coming into picture? Okay, so, but for that, what we need to understand is in the practical system, or like you might ask me a question saying that we are using mobile phones, the signal travels much faster, so this delay could be very small, right? So what would be the delay in practice? So this T max would be around, I would say, let's say 2 microsecond. 2 microsecond is very less, but let us try to see the other parameters, why this is making a big difference. Okay. So to understand this, what do we need? So I'm just trying to explain some the very basic things. I'm not telling any complex complex equations or complex diagrams, right? So what is the thing that we need? That is T symbol, which is symbol duration, one symbol duration. Okay. So what is the relation to this symbol duration? So it is inverse of the bandwidth, BW. Okay. So let me just try to write that. Okay, one symbol, whatever I had written in the previous slide, I'll go back here. What is T symbol here? So this point, right? This point is T symbol. So this will become T symbol. Now to understand what is the value in practice, okay, in your mobile phones or in practical system, to understand this, we need to know bandwidth. So one important aspect is, let's say you're in 2G or 3G. Okay, what happened is the bandwidth considered was, let's say, 100 kilohertz. I'm taking some rough numbers so that it matches we can easily calculate the things. So bandwidth is 100 kilohertz. So with bandwidth 100 kilohertz, what is the symbol duration? Can someone tell? So 1 by 100 kilohertz, right? Yeah, go ahead. 10 to the power of 10 microseconds, we can say, right? So 10 microseconds is your symbol duration. Now this was present in, I was telling, let's say for example 2G, okay, for example 2G or 3G, this is the bandwidth we are using with 100 kilohertz as the bandwidth. Now another thing, based on your like daily usage, what is that you look for as an end user? What do you look for? So you look for higher data rate, correct? So you need to download more documents, files. So you need more data per day, or you want to play online games, things like that. So one important parameter which we need to consider is the data rate. So how is data rate dependent on the bandwidth? Okay, so I would say it is directly dependent on the bandwidth. Okay, so which means that if you have just 100 kilohertz, your data rate is also approximately in terms of kilobits per second. Do you really appreciate in your mobile phone or in your, like, while downloading a movie, for example 1 GB movie or thing, so it is downloading in the kbps, do you appreciate? No, right? It will take time, and you don't want that to happen. So then what has to be done? So one of the important factor is we need to definitely increase the bandwidth. Okay, this bandwidth we need to increase. So how much shall we increase? How much speed do you want? Like you want in terms of, let's say 5 Mbps or 10 Mbps, which is, let's say present today. So in which case, let's say you need let's say 10. To make it simple, I will say this is replaced with 1 Mbps. Okay, so I made it 10 times, which is 1 megahertz. 1 megahertz as the bandwidth. So if 1 megahertz is the bandwidth, you can expect your data rate approximately in terms of megabits per second. Okay. Yeah, what is the observation here? So the moment I used T symbol, the bandwidth 100 kilohertz, I got 10 microseconds, and now I'm using another T symbol based on the new value, that is 1 by 1 megahertz. Now what is happening? What is the T symbol duration? So this is a straightforward 1 microsecond, right? Yeah. Now can we compare these two values with respect to what do we have in the T max? Okay. So the thing is that what was the T max? T max I consider it as 2 microseconds. Okay. So what is the T symbol 1? We had got 10 microseconds. Another T symbol 2, we had got just 1 microsecond. Now what I will do, I will draw the same diagrams considering these two. Okay, and this is the T max which we have. Now with 1 microsecond symbol duration, so this is, let's say, 1 microsecond. In 1 microsecond I will transmit x1, first symbol. So what about second symbol? In next 1 microsecond, which means by the end of 2 microseconds I will transmit x2, second symbol. Then third, fourth. So 4 microseconds is here. Now the thing is that 1 microsecond is present over here. So if I take the max delay as 2 microseconds, then can we draw the picture? So 2 microseconds means the first symbol will start from here. So this is first symbol considering this delay of 2 microseconds. So which means that 2 microseconds is 1. So at 3 microseconds we have x1 and then x2. Now what can you observe? Here you can observe that when there is this x3 third symbol, here you have x1, which means that total you have an intersymbol interference of 1, 2, 3. 3 symbols would be interfering because this is 2 microseconds. Then you can think of intermediate path as well, which is actually delay of 1 microseconds. So in total here you will have an intersymbol interference with the 3 symbols. Okay. So that you can see that x3 is interfering with x1, which means that you can say 3 symbols worth of information is having interference. So did you see, like, what is the challenge here? Like the challenge, okay, let's look at the other one, which is T symbol 1. So that says that my one symbol is 10 microsecond worth. So which means that this, I will try to write here. So the 10 microsecond worth, this much is T symbol, which is 10 microsecond. Okay. So this is x1. For that much duration I am transmitting symbol x1. Next, what I have to do, I have to take the other part. This is the first part and this is the second part information. So in the other path I had a delay of 2. Can you see here 2 microseconds delay? Considering the same delay here, 2 microseconds I delayed and I transmitted the x1. If you see here, actually not many symbols are interfering. If you only when you see x1, majority of the x1 is also visible, and you're not seeing the interference from the other symbol. Let's say now here x2 is there. Okay, x2 is started from here. For x2, only for the duration of this 2 microseconds, you have that interference from the x1. Here how many symbols are, let's say, interfering? Two symbols are interfering, first of all, two symbol ISI. But the thing is that even the portion of interference is very small. But whereas in the previous one you had interference worth of three symbols. Okay, so what can we say from this? The thing is that when you try to increase the bandwidth to increase your data rates to meet your requirements of having a faster download speeds and upload speeds, when you increase the bandwidth, your symbol duration is coming down, and when the symbol duration is coming down, you just saw the phenomena that more and more symbols are getting interference. Okay, so having understood this problem, that is when it is decided that yeah, we need some new technology where we can overcome this kind of problem so that we can have a reliable communication between transmitter and the receiver. So till this point, understood? Any questions? Any questions from anyone? Okay, so having understood this problem, let us try to see what we can think of. Okay, so the first one is, see, as I was telling, one main requirement is, let's say in the earlier case, the bandwidth is just 100 kilohertz. Okay, you're not happy. You're not happy here. So what you wanted is, you wanted a larger bandwidth. So you went for 1 megahertz. But 1 megahertz, we saw the problem. There was a lot of intersymbol interference. So what can you think? What do you think about this particular diagram? Like if you want to have more and more information to be transmitted without having a problem. So one thing is, you can think of the situation like, sir, you take the same thing, 100 kilohertz. You take the same thing and you keep stacking it instead of the one bigger bandwidth. So what will happen? You take 100 kilohertz, and can you stack the other one immediately after this? No, you know about this concept already, right? Which is a frequency division multiplexing. So that is nothing but just a FDM. Okay. So frequency division multiplexing, definitely after one band, you need to have a guard band because of filter roll off and things like that. So here you cannot actually go for this one. You need a guard band. So I've written the guard band, and then you are going for another 100 kilohertz. So like that, if you are going to transmit in smaller bandwidth chunks, then actually it's like your symbol duration is getting down, and then you might say that yeah, you will not face the problem. But with this, yeah, it solves the problem. There is no doubt about it. But it actually brings in some more challenges. Okay, what are those challenges? First of all, you should have this guard band. For that, for each and every band, you need to have a filter. Okay, for every band you need to have a filter, and your hardware component is getting increased. There is another requirement from all of you, right? That your mobile has to be as much compact as possible, and also it should be of a very low cost, right? If you try to incorporate more and more hardware to accommodate such a technology, then what is happening? It is becoming bulkier and as well as costlier also. So which is not very much intended. So now what should we do? And moreover, the problem is that since you're giving this guard band, right, you're wasting this much bandwidth. So here, instead of accommodating, if you say 10 kilohertz, if I want to accommodate it side by side, then it will become 10 bands as such. But since there is a guard band, you need to give guard band instead of 10. What can happen? You might accommodate just 8 bands. So can you see here again? It is actually reducing the required data rate or required bandwidth. So any questions? So there are no questions, and you completely got it. Is it? So to overcome this, what has been taught in the current existing literature? So you take that smaller bandwidth, let's say 100 kilohertz, and try to take the another band such a way that it is actually orthogonal to the first band. So another one is orthogonal to the third one is orthogonal to both the previous two bands. I mean, what does that mean? When do we say that okay, these two are orthogonal? Like in the sense, for the first band, when there is a peak, the information from the other band should be almost zero. Okay, can you see here? Like for the first band, when it is at the peak, the second band is becoming zero. Similarly, the for the third band as well. Third band actually, I've not written the complete, but let's say this is a sync function. So it goes like this, and even the third band is becoming zero at the peak of the first band. So this you got it like if we bring in such an orthogonal bands, then we can try to pack more bands within the given complete bandwidth of let's say 1 megahertz in our case, and then you can have a better communication, right? So we can eliminate that whatever the intersymbol interference we saw. So for that, what has been done? How can we choose the orthogonal band or orthogonal signal? So this particular band has to be carried by one carrier frequency, right? So let's say that carrier frequency is f1, and the second band carrier frequency is f2. So f2 is chosen integer multiple of f1. Okay. So for example, in simple words, like you take a cos 2 pi fct. This is fc1t. Let's say carrier 1. Then you take a cos 2 pi to fc1t. Okay, so cos fct, cos 2 pi fct, and cos 2 pi 2 fct, these two are orthogonal to each other. This is from the basics of signals and systems. Or otherwise, to visualize that, you need to draw those two pictures. Okay, so what is cos f1? So let's say something like this. Okay, then 2 times f1 is its frequency is doubled, which means that in the same duration, 2 cycles should come into picture. So it would be one cycle, another cycle. So this is like f1, this is 2f1. Okay. I've shown sine signal here for the sake of simple understanding, but the same thing can be written for cos as well. Okay, now if you carefully observe, like when there is a peak, okay, there is a zero from the other carrier. Okay, and also when we have a peak here, then there will be corresponding zero. So basically, if you take one period, you take this one complete period, integrate over one period, and you say cos 2 pi f1t and cos 2 pi 2 f1t. Okay, if you integrate over this one period is actually in this case should be the symbol duration. Okay, so in this duration, if you integrate and if you take this picture and if you try to integrate, what you should get? You should get 0. If you get 0, then what we can say, these two signals are orthogonal to each other, right? So is this clear? So with that, actually, this OFDM concept has brought in, because earlier we saw that okay, there is an FDM. So this FDM had problems, but now to overcome the problems with FDM, we now introduced that our carriers should be orthogonal to each other. So that is when this FDM, this frequency division, we made orthogonal frequencies. So finally we brought in the concept of OFDM. Okay, so this is clear. But I would like to give one more picture to this. Okay, so that picture is from the band. Let's say we had considered we want 1 megahertz, right? So 1 megahertz band, in this band, this is let's say frequency response. So in this frequency response, we need that the response is almost flat here. Okay, this should be flat for the entire bandwidth. Then we will be in a position to recover the signal very well. Which means that here there is no ISI. But we saw that if you want to go for 1 megahertz, there is a huge ISI. Right, many symbols are interfering with each other. With that, what is happening? This is not flat. Like this would look like at some point you have you're losing your flatness, and your signal is having a huge ISI. Okay, but if you carefully observe, I mean, to understand the concept, if you try to physically interpret from the diagram, let's say here you try to take a small portion of the bandwidth. So this is a small portion of the bandwidth. Then you would see that here the channel would look flat. Okay, even though if you look for a wider frequency, it looks that it is not flat. But let's say if you look for a small portion of the bandwidth, then it looks flat. By that way, also we can eliminate the intersymbol interference. Okay, so what has been done in the OFDM? So in the OFDM case, this entire bandwidth, okay, 1 megahertz, is divided into this smaller chunks. We call it as a subband. Okay, this subband will have a smaller bandwidth, and this how many subbands we can consider? That is one question. So you can say I'm telling the smaller band, right? You can think of very small, but again you will have a lot of problem with choosing a very small that I will not touch upon right now. But you think that one number has to we need to arrive at one particular number to design the optimal subband size. But for now, in our case, we will consider it as 100 kilowatts, which we had considered. Okay, so which means that we can accommodate 10 subbands. Now, this 10 subbands, what I was telling, rather than you transmitting it with okay. Now, I need the support of one more concept that is nothing but single carrier and multi carrier. Okay, in single carrier, what do we do? So this, let's say, this complete 1 megahertz signal. This will be carried. Okay, this signal from your mobile phone, it will be carried using the center frequency, right? Or what is the other layman name? The carrier frequency, right? Because it carries the information. We calling that particular frequency as a carrier frequency. So what is the carrier frequency? So that carrier frequency usually it will be in terms of gigahertz, 1 gigahertz or 2 gigahertz, right? Even in your mobile phone. So today, if you take a different operator like Airtel or Vodafone, you will see that okay, it is in terms of gigahertz or 800 or 900 megahertz and things like that. Now here you're using one particular carrier to actually transmit or carry the information. So since you're using only one carrier and entire signal processing blocks also we have designed as if it is single carrier. So that forms the single carrier system. Okay. Yeah, here the basic concept is what do you say about the basic concept? The basic concept is when we say signal is carrying, then it's like in the beginning the signal will be in the baseband, which means that center frequency is 0, and this is a well-known picture to all of you, right? And now this has to be carried to the higher frequency, means let's say FC is equal to 1 gigahertz. The entire information has to be put in around this 1 gigahertz. Okay, so basically from year to year frequency translation is happening. That is again a very important property of digital signal processing. So if you want to have a frequency translation, then especially okay, this frequency translation I'm talking in which domain? Like it's in the frequency domain, right? I'm telling this spectrum, which means that frequency domain signal should be moved to another one, which means here I'm doing x of f minus fc. If frequency domain signal has to be formed processed in this way, then like first of all, how do we get the frequency domain signal? The frequency domain signal you will get it by forming FFT, right? So which means that you have x of t, the time domain signal. So what do we need to do with the x of t? We need to have this exponent component. So e to the power of j 2 pi fct, right? So if you perform an exponential multiplication with respect to the center frequency to the time domain signal, it is as good as do you performing the frequency translation in the frequency domain. Okay, so this we need to perform in the time domain. So by the way, this is ensured, and if this is ensured, which means that using the single carrier, you are carrying the entire 10 megahertz bandwidth information. Okay, now with this supporting concept, what do I need to talk about OFDM? Okay, so OFDM is like we have divided this entire bandwidth into smaller chunks, right? We have divided smaller chunks. So I was telling, okay, this you transmitted with frequency f1, this with 2f1, this with 3f1, like that. Now we need those frequency translators, right? With this f1 to f1 like that to actually shift your signal or to carry the information. So what is that? What is that we need to do? I will take the simple thing. So it was like this, right? So it was like this: x of t, you multiply with the exponent e to the power of j 2 pi fct. So this has become x of t to the power of j 2 pi fct. Okay, in the earlier case, single carrier case. Now with this case, it's like you take x1 of t because across each subband you are transmitting different information, x2 of t. Then you send it to multiplier and e to the power of j 2 pi f1t, and then you transmit it. Okay, so then it is becoming like okay, x1 of t e to the power of j. Yeah, think of some questions here. We're able to. Yeah, you're able to get this right, that in single carrier we wanted that one multiplier, whereas when we go for OFDM we have many subbands, right? For each of these subbands we need that many multipliers, which means that what's happening, like in our case we saw that we need 10 subbands, so definitely we need 10 such multipliers, and for generating each of these frequencies we need local oscillators. So again we are actually bringing in the problem that we are increasing the more and more hardware. Getting this point? Any questions here? Okay, so in simple things like we wanted more and more hardware to have this thing, right? So which is not intended actually. So then what should be done? So if you carefully observe, like, okay, I will write this equation as well. Maybe I will write it here. So x1 of t e to the power of j 2 pi f1t, okay. X2 of t e to the power of j 2 pi f2, but f2 is 2 times f1 of t. So that is when actually it was the research was done, and it was figured out that what if we do such kind of operations rather than in hardware, if you want to try to do in the baseband or digital domain. Okay, digital domain means before even doing your digital to analog conversion, or let's say now we have analog signal, we have written analog equation, right? If you want to have a digital version of it, what is that we need? So sampling, how do? You replace t with NTS, right? So now how do we get this f1? So f1 is, how do we get this f1? So we have this in the entire band we have this subband bandwidth, right? So let's say that subband bandwidth is delta f. Okay, so then if you want to get f1, then definitely this. Okay, first of all, how can we write this entire bandwidth, which is let's say 1 megahertz, right? Here in this case, so I would say this is complete bandwidth. Bandwidth is equal to number of subbands. Okay, I will say number of subbands into delta f. This would make this bandwidth. So number of subbands here I was telling 10, and here in this case delta f will be 100 kilohertz. Okay, so one band we consider 100 kilohertz, and number of 10, so it will become 1 megahertz. Okay, now how do we get f1? F1 we can get it as just delta f divided by, yeah, how much is it? So here sorry, not delta f. So the complete bandwidth, okay, complete bandwidth you divide by number of bands. F1 will be bandwidth divided by n, right? If you want to get to 2, then 2 times this bandwidth divided by n. That's how you'll get 200, right? Now the thing is that if we want to write in general, it's like fk is equal to k times bandwidth divided by n. Okay, let us go back to our equation here. Okay, so now you substitute this. Okay, now I want to write this in a generic way. So how can I write? This is like it is this time domain, and t is replaced by n, so I will write x of n. Then e to the power of j 2 pi. This is like, in general, what I can read is that fk, right? Fk, and t is replaced with NTS. Now, what can you observe? Finally, when we have these two subbands, I mean to transmit them together, we'll be adding, right? We'll be adding and sending it. So which means that to this we need to do the summation. Which means that if I want to do summation, this is like 10 bands. So what I would say, this n is equal to 1 to capital N is equal to 10. Okay. Sorry. So n is equal to 1 to 10. N will be is equal to 10. Yeah, here you can say this is n depends on these samples, and this is how the equation comes into picture. Okay, I think you guys are able to see. So there are much more mathematical expression. Okay, further, but if I start reading, it will take time. So I will directly take it from my notes and I'll try to explain. So in simple, yeah, I just touch upon a few points which I have just explained. So as I was telling, like. Yeah, subcarriers, right? So we need to divide the entire band into n subbands. So that equation we saw, and we had formed this equation, which is that the multiple subband information, we take it like this, where we saw the frequency translation property, and then finally we need to add all these subbands to form the final OFDM signal, right? And with this, since the subcarriers are orthogonal to each other, what did we see? We also saw the orthogonality property. Yeah, even we can actually, prove that with this particular kind of equation, because we saw, right, that we need to apply that frequency translation, which means that we need to multiply the time domain signal with the exponential component. So you take the first exponential component of the first subband, and you take the other any other subband exponential component, and over one period which is shown here. So if you try to integrate, as I was explaining, you should get it as 0. Then they will be orthogonal to each other. Okay. If you take the same band, then you should get 1. If you get the other band, you should get 0. Okay. Yeah, so with that, then using the different sampling rate and modifying the equations, what we had seen this expression, right? We had seen this IDFT expression, IDFT of symbols, and as I was telling, to implement that in the practical system, because IDFT is very time consuming, there is a faster algorithms that are defined, which is IFFT. So if you actually take that into account, then we should okay, first we'll try to see the basic block diagram. With this understanding, what we can say is, let's say I want to transmit x0 x1 till xn minus 1, because now I'm taking n symbols because we have n band. For these n bands you take n symbols which are to be transmitted. Then first what do we need to do, like you convert that this serial data into parallel data. So this is one block which we need, and then you perform IDFT, because that's what we just derived instead of using this local oscillator and multipliers, and then you convert back to parallel to serial. Okay, so then you transmit over the channel. This becomes your blocks in the transmitter part. Okay, and at the receiver part we need to actually perform the reverse operation that is shown over here. So but finally, as I was telling, what do we need to do, like we need to replace this IDFT with IFFT and this DFT with FFT. Okay, yeah, so this is one important aspect which I wanted to mention, like since we want to write the mathematical expression, right, first we should understand how we can write the equation in that channel environment where it will introduce intersymbol interference. Okay, so I had shown the block diagram. I mean, I was trying to draw the signal diagram, right, between one symbol to other symbol, how actually, the second symbol is interfering with the first symbol, like that. So if you write the equation like that, so this is y of 0. Okay, at y of 0, you should receive only signal corresponding to x of 0, right? But what is happening, because of multipath components, you not only receive the signal x of 0, but you are receiving previous signal. Okay, previous signal is xn minus 1, xn minus 2, like that, till you consider how many channel taps, that many channel taps you will receive the signal. Okay, so here you are considering channel taps L, let's say for example last time like 3, which means that you will have x of 0, x of n minus 1, n minus 2, n minus 3, like 3 components you will have. So if you write I mean, for y of 0 you have written like that, but for y of 1 also we can write the same thing, right? So y of 1 we should receive x of 1, but you will also receive the previous one, which is x of 0, then x of n minus 1, like that. So finally you can write this y of n, because we have considered 10 bands. So for all the n bands you take it, n sub bands you take it, and you can write down. Okay, you can write down this equation. So based on the diagram, I hope this is simpler to write. Even I try to explain like why we need to take this extra component in the equation. Okay, but if you carefully observe this, okay, this would look like a sort of circular convolution of h and x. Got it? So we understood it. It looks like this. Now what is that we need to think of? Like this is in the time domain circular convolution, but if you take the FFT of it, then it would become just the convolution in the time domain. It is just a multiplication in the frequency domain, right? So it would result equation something like this, that your h and x are just multiplied in order to do any convolution. So with that, I want to enter is the matrix of approach to this OFDM. Okay, so whatever equations I had shown, I had written over here for all the n symbols. Okay, so this is for all the n symbols in the sense that n subbands. So this is how you're gonna write this. This has incorporated the ISI. Okay, now the thing is that you write this in a matrix form. So writing this in a matrix form, yeah, you can easily arrive at this if you give some time, but I will not go through that on how you should be writing this. If you carefully observe this, okay, what we can observe is, if you take this first column and if you take the second column, h of 0 is shifted, right? H of 0, h of 1, h of 2, h of 0, h of 1, like h of 2 it will go on. Whether you take column or row, you will see that this row is shifted by each and every row is shifted by one value. Okay, and this H matrix is looking like a circulant matrix. So it forms a circulant matrix. So once you write this circulant matrix, then there is one important property. Okay, that property is nothing but I will just write it over here. That property, let's say H is a circulant matrix, right? H is now circulant matrix. So this circulant matrix can be written as I will say F Hermitian, okay, then H D, then F. Okay, now let us talk what is this F Hermitian. Okay, F Hermitian is nothing but, this is nothing but your IFFT. Okay, so this is HD is your diagonal matrix. HD is the diagonal matrix. This F is nothing but your FFT matrix. So this HC, which is a circulant matrix, which I had just shown, that can be decomposed into these three matrices. Okay, these three matrices. So here in these matrices, so you can clearly see that this IFFT is there, FFT is there, and that is very much required for our even OFDM, right? So this is also giving an indication that if you form the circulant matrix into diagonal matrix, which will help us to convert to the frequency selective channel to the flat fading channel, then we need this IFFT and we need this FFT. It just actually confirms that particular concept that yeah, we can implement using this IFFT and FFT. We can implement the OFDM. Okay, so to just showcase. So if we apply that property, then you can see that my received signal y1 to yn, you can write it like this transmitted signal x1 xn should be the IDFT of this x0 till xn. So that's why at the transmitter we need to perform IDFT, means IFFT of x you perform. Then this channel, okay, this channel will be HC. Okay, but now because of this decomposition and because of applying this IFFT and FFT, this channel is shown here as a diagonal, right? So now this channel is diagonal matrix, so that you will see that across these y0, y1, across these subbands, you will have the signal which is intended. So got it? Any doubts here? Okay, is this clear? So what did we just do? Like in the time domain, we had considered right equations. Where we were considering that each and every subband we had an interference. We not, like for example at y0 we not only had x of 0, but we also had x of 1, x of n minus 1, n minus 2, other symbols. But now with this application of IFFT and FFT and using this property of circulant matrix, we saw that at the receiver side, this is the equation we are going to get. So or otherwise, if you see here from this matrix, y of 0 will be just h of 0, because all the other elements are 0, only diagonal element is there. So y of 0 is equal to h of 0, and if you see here, you will get x of 0 only. So y of 0 is equal to h of 0 into x of 0, which means that at subband y of 0, we wanted only x of 0, and that is what we got. Okay, there is no ISI introduced here. Got it? So in general, that is what the equation written over here, y of k is equal to d into x of k. So by that way, your ISI is reduced, and you are able to recover the information present on each and every subband without any interference, without any problem. So I hope the matrix approach also you got it for this OFDM. So any doubt till this point? So why do we need like this channel estimation? I mean, we understood that when the signal is transmitted over the air, right? Because of the environment is changing, like signal will travel and it will have an obstacle and it will reach to the receiver. But that obstacle might be constant or might not be constant, right? And also let's say you're traveling in a car. Then if you're traveling in a car, then every time the obstacle could be some other building, not the same building, right? So in that way, channel is changing, and that's why we need to actually estimate that channel. If you know, okay, this is my channel, this is the properties that it is having, then actually we can nullify those effects that are introduced by this channel, and then we can recover the information which we wanted. Which means that like I was just writing this equation, okay, y of 0 is equal to h of 0, x of 0 I have written. But where is this channel information we are embedding? This one, right? H. So definitely what we transmitted is x of 0, like whatever you talk on your mobile phone or the file which you want to transmit, that is coming as part of x of 0. But this h is for channel. Definitely we don't want this, right? So if you want to eliminate this, in the first place we should know what it is. So now coming to the I mean, I will write just in a simple way that y is equal to hx. Okay, let's say this is just one equation. So here, how many unknowns are there? First of all, see, whatever we talk, that is not known to the receiver, right? Receiver is far away. So definitely this x is actually unknown to the receiver. It has to actually decode and say, okay, this is what the transmitter said. Okay, he has said hello. Yeah, the receiver also reproduced it as hello only. Now, this is unknown, we got it. What about h? H is also varying, right? Very frequently. So h is also unknown, which means that we have these two unknowns here, and there is only one equation, difficult to solve. So then what do we need? So we need first time like okay. So we need first time like okay. We should know this x in order to determine h. So x, it is called as pilots, okay, or reference signal. This is known to both transmitter and receiver. in the beginning itself I will tell, hey, from my side I will transmit this known signal, and at the receiver side also you use the same known signal, and by that way you can derive your H. So then now what happens at the receiver side? I mean, I'm just giving the simple equations. So there are many other estimation methods and things like that. So in simple words, I mean, if you want okay, so if you want H, okay, H I will say estimation, then you divide Y by X. I will say X pilots. Okay, this pilots are nothing but this XP. So then you got your H, right? Now use this H, and now let's say in the other instance, this is transmitted. Now you want this X. Now you already estimated this one, right? So now use this, and now you say you want your X estimation. Then use your Y by H estimation. Then you will get your X. Now got it? But now how that should happen? So I was telling about symbol duration, right? T symbol duration so symbol x1, symbol x2, symbol x3, like that. You need to send all the time the data, whatever you talk. Like let's say if you're sending it to 10 times, okay, 10 times, then in that case, one time you transmit the pilot XP, don't transmit the data. Then you tell to the receiver, okay, in the second symbol I have transmitted pilot. You take it and estimate the channel, and then you use this estimated channel across x1, x3, and x10 to get back your data x1, x3 till x10. Okay. So simple, right? Channel estimation, you got it. So got it, right? This simple concept, channel estimation. But now you might ask question that, sir, I am traveling faster speed. So you said in the second symbol you had a pilot, but you're using this in the 10th symbol, which means that after like 10 microseconds, channel will change or not, like that. Okay. Again, there is one important concept in the wireless communication. That is nothing but TC, which is coherence time. Okay, this coherence time tells that for how long, okay, for how long the channel is constant. So channel constant duration, let's say. So this might say that, hey, my channel is constant for a duration of 10 microseconds. If it says like that, then definitely whatever you have estimated your channel here, okay, H estimation in the second, which means that I will say at 2 microsecond, you can use this for the next 10 microsecond duration. So definitely, which means for the next 10 symbols, you can use the same channel to get back your information. Okay. So this also got it, but I will not go through on how this particular TC would be derived. Definitely one parameter what I can say here is this coherence time depends on your just now I was telling, like you are traveling in a car, then channel will be changing, right? So how fast, if you're traveling so fast, channel is changing so fast, so then your that duration would come down. So one parameter is that it depends on the speed of your mobile phone or UE. So any questions here? So till this point, do you guys have any questions? So you can even ask any basic questions based on based on what you're using in your mobile phone. So let me see whether I can answer. So it may not be from this particular, let's say, whatever concepts I had taught. Maybe in generic with respect to wireless communications also. Yeah, think of some questions. Is it placements are done or it's yet to happen? Going on. So any wireless companies which are coming? So nobody is giving interviews to those companies? Sorry? So which is your usual one which is coming in the wireless domain? Capgemini, right? Yeah, so I mean, whatever the concepts that I have explained, right, in this particular module, okay. Actually, I had created a YouTube channel, okay. So especially whatever the concepts that I have covered in the playlist 3x, okay. If you guys are interested much more, and if you want to understand in deep about those equations, I mean, you can go through this OFDM concepts series, okay, in the YouTube channel, and at various other colleges, so whatever 5G related presentations I have given, it is present over here. Even for the last time to your seniors, I had given OFDM and MIMO both 4th and 5th module. So that presentation is also over here. Like if you want to understand the fifth module related to diversity and things and all the basic concepts there, you can go through. Apart from that, yeah, I don't know, many would be interested in AI/ML related, so that is also present for 5G or 6G. So how you can actually leverage your AI/ML skills in the wireless domain. Yeah, even for like, let's say you're giving interviews for wireless companies, have prepared this interview question and answer for telecom industry. You can go to that, and there is one more. Yeah, one more this playlist is there which is related to job switch. Okay, so this job switch will help you to know, understand, okay, for you, if you really want to work in a wireless domain, like where all, which all companies are related to wireless domain, and where do we have openings, and for that, what are the things that you're supposed to prepare, and all the things I put up here. I hope that would be very much helpful to you guys. So this is the channel. Yeah, if interested, you can go through. Yeah, OFDM concepts playlist I just opened, like yeah, it has got some 10 14 videos, I think. All are short videos only, like around 9 minutes, but if you watch it at 1.5x, these are all like some 6 minutes videos. So you can cover the entire fourth module, I think you can cover with these videos. Okay, so with this I think I will wind up for today's session. Thank you. If there are no questions, thank you very much.